I will briefly mention about the background, how we generated this project, and then why the agriculture is important. And then microRNA gene regulator network, usually I'm talking about this. This network supports functional characterization of the specific transcript factor, which is involved in plant architecture and plant stress responses. Also, how we generate the transcript factor resources as a model plant in Arabidopsis root. And then I will move on our focus on the microRNA root regulatory network. And then we try to use a lot of ways to validate this gene regulatory network. So genetic screening and in vivo tobacco system, and using the genome-wide scaling, we use a small RNA library and RNA-seq library. And also, we based on this gene regulatory network, we want to focus on specific transcript factor. So I'm mostly interested in gene finger mailbox transcript factor. I will mention about this. And then more like big view of this project is evolutionary aspect and crop species. I'm already working on the maize. I will mention about this. Actually, Doreen Whale Lab is quite interested in plant architecture that impacts in traits. So mostly we are focused on Arabidopsis thaliana as a model plant, and sorghum, and rice, and maize. As you see here, in crop, maize, rice, wheat represent 50% of the human intake, calorie intake. It's directly consumed by human beings and indirectly as livestock feeds. And this is very important, but I'm talking with the people, I'm working with plant biologists, and people usually ask to me, how do you improve the crop yield? Because crop yield is very important role, because none of the people can eat without one day. So it's very important. So to improve the crop yield, one of the key factors is environmental stresses, like abundant stresses. So one of the most significant factor is water deficiency, for example, drought stresses. As you see here, in the normal condition of the farm, in the dry condition, as you see here, leaf morphology is tall, plant morphology is totally different. And then this morphology is directly impacted on the crop yield. This is maize, corn, and this is ear. Actually, this is plant size is directly impact to get our crop yield. And also the plant size reduction and this fertilization is a problem. Finally, there is embryo abortion, so you can get any kind of ear in severe drought stresses. So you remember 2012, there is a huge drought impact worldwide in the US. So as you see here, 2012, in the corn yield is dramatically dropped. And this is directly impact in the economical situation in the US. So our question is how we grow enough food to feed the world. So in the worldwide, rice and maize is a primary crops. So as population grows, the needs for the cereal crops, the demands for the cereal crops does too. So as you see here, for over 400 years, the human population increased more than 10,000-fold increase. How we feed a person? So to solve this question, therefore we have some strong knowledge background of plant biology. So kind of system level of information and molecular mechanisms that regulate the development, as well as how they respond to stresses like environmental fluctuation. So in this view, and Doreen Whale Lab have an interesting project is going on, Brian project. I will briefly mention about this. Grabbing information about 28 species genome sequencing information, and they include 15 molecules. So they include rice and wheat and corn. And also, not only this is monocle 15 molecules, they also information of 9 core eukaryotes. So they all have Arabidopsis thaliana and tomato and populars, etc. So this Brahmin, the Brahmin website provides you a lot of information, not only the genome information, but also there is a lot of QTA data analysis and a lot of ESD data sets, and then signaling pathway and pathogen-related signaling pathway. So you can go to the website and see how many information there are. So not only this required dipot information, mostly they also include four lower plants: moss and spike moss and green algae and red algae. So this is a lot of information they have, but mostly people are interested in crop spaces. So crop spaces, as you see here, we have corn, soybean, rice, wheat, and potato and tomato, and also their progenitor. So using this information, we can do further research analysis and studies going on. But today, I'm more focused on the modern organisms. We have different kind of modern organisms information there. So one is Arabidopsis thaliana. First, it's well explained about Arabidopsis thaliana floral structure. Now I want to talk about Arabidopsis mainly in Arabidopsis root, but later move on to the floral structure. So Arabidopsis thaliana is very modern organ, and Brachypodia we use as monocot as a model plant, and the Vericarbo and the lower plant. And as Arabidopsis thaliana, I will briefly mention about why we choose Arabidopsis thaliana as a model plant. Because Arabidopsis thaliana is very little small plant. It's a weak plant, and this small size is very fit in the closed chamber, and then small limited space you can grow many plants. And then the life period is very short, in 2-month period, and so you can get harvest within 2 months, and then again you can planting again, and then you can single plant and then harvesting a lot of seeds. So the seeds in one plant a lot of seed production. So and so it is good for the genetics, study on the genetics. So at the relatively small genome scale, so you can use this is very simple model. So this is Arabidopsis thaliana. So this is root. If you transfer section with up to down, so you can see the beautiful cell layer. So Arabidopsis thaliana is a beautiful system to study of time and space in a single organ. So as you see here from the epidermis, from the outside, and the cortex, endodermis. Inside of endodermis, there is still organ. Still organ composed of 3 different cell layers, and the pericycle, and the xylem, and phloem. Pericycle is very important because they are localized in the center of the root. Not only the structural formation, they have something specific function. Pericycle especially, they are able to divide it as metastatic function, and then they also higher plant, their lateral root is initiated in the pericycle zone. And also they uptake water from the root and uptake the nutrient from the root. It's very important. So we choose the Arabidopsis root in the initial project is going on about this. Initial project is collaboration with the field benefit group because they have a beautiful expression profiling in single organ. So they use 19 GFP tagging lines, and then using the cell sorting system, they collect all the expression profiling and specific tissue expression profiling. As you see here, it's endodermis and blood hair cell, and then crystal center in the root, you can see the beautiful expression profile. This is first microarray data based on expression map of a single organ. So we can collect the spatial expression profiling and then temporal expression profiling. The temporal expression profiling, you can divide it group by transversion section, 13 different transversion, and then you can extract the RNA and then send it to the microarray. As you see here, you have beautiful dominance mapping here by tissue-specific expression pattern. So it's very interesting expression profiling, and also they have a temporal transcription profiling. As you see here, from the tip and the mature, they have a longitudinal axis, 40 different diverse distinct patterns we have. So we have this expression genome-scale gene regulator network. So we are quite interested about microRNA and transcript factor because microRNA and transcript factor is primary regulator, and microRNA is a non-coding RNA. It's very small, little, tiny nucleotide, 20 to 25 nucleotide, and then that is play an important role during the plant development and stress condition. Also, they are impacted the nutrient degradation. And microRNA, whereas microRNA, people mostly focus on microRNA targets, but not, many of the studies not studying on the upstream of the microRNA. For example, transcription network that regulate the microRNA expression itself remains largely unknown. So that's why we just more focus on this upstream region. So what we can do is we use transcription binding to specific microRNA promoter and then transcription factor promoter. And then we call this is PD interaction, protein DNA interaction. We use EC1 system. Also, we want to incorporate the other public database, mRNA and microRNA interaction. We call RR interaction. And also, we collect all the public database, protein-protein interaction, PP interaction, using the RR-cis interactor mapping consortium. So we want to try to generate a huge gene regulator network. Before that, I just mentioned about what we are doing. So we use EAST-1 hybrid system to map the gene regulator network. So EAST-1 hybrid system is very it's a gene-centered approaches for mapping PD interactions, and it's rapidly it's beautiful system, powerful system to rapidly identify the transcript factor that bind to the specific DNA of sequence what we are interested in. So previously we published it in EAST-1 hybrid assay. So we use two different methods using the EAST-1 EAST. So two different methods, transformation method and naming system. And also we use two different reporter system, LogG and P3. As if they are really binding, they have different color. They show it like here, and then we have the redundant, the four different redundancy. Like this, we just try to map the gene regulator network. Our initial focus was to develop the transcript factor resources. They focus on the Arabidopsis still. So we collect as whatever we can clone a transcript factor in Arabidopsis. We collect all the transcript factor which is enriched in the Arabidopsis. So we collect almost 950 transcript factor. This is probably almost 94% still expressed transcript factor. Also, we try to clone the gene promoter region. It's almost we have over 100 microRNA promoter, and the rest of the 57 is the transcript factor promoter and target microRNA target. So using this, we generate a huge integrated microRNA gene regulator network. As you see here, we generate 8 data sets. So we find over 3,700 edges and more than 700 nodes. So how we symbol this one? If one transcript factor, we just symbol as a round one. And the microRNA promoter and transcript factor promoter is a square and a different color. And the target is yellow color. And the edges, if there are EAST-1 hybrid binding, there's a PD interaction with blue color, protein-protein interaction with is using the EAST-2 hybrid system, we colored like orange color. So microRNA mRNA target is just pink color. So we generated this microRNA gene regulator network. This network includes 52 transcript factor family. So first we wanna using this gene regulator network, we wanna explore the topology of the network. So I would like briefly mention about the topology of the network because to simplify the microRNA gene regulator network. If you simplify the microRNA gene regulator network, we usually distribution of the incoming connectivity. So we usually call injury. Injury means specific microRNA, multiple transport factor, or single transport factor is binding to the specific microRNA promoter or transport factor promoter, as you see here like this. And then it's one example is microRNA 158B. As you see here, multiple transport factor binding to the microRNA 158B, but a lot of those transport factor is binding here. But if we overlay with the expression profiling cell sorting, and then even though there's a lot of those families binding, but they are different family. So that indicated that this dog family is enriched in different cell area. It's quite interesting. And the other way we want to present the topology of the network is ultimately. So ultimately is one specific promoter binding to the multiple microRNA promoter or transport promoter. So as you see here, we want to draw the graph here. So most of the transport factor binding to the less promoter, one or two promoter, but few of the transport factor is binding to multiple promoter. So this is quite interesting. The one single transport factor binding to a lot of microRNA promoter. So we are quite interested in this one. So later I would like to more talking about this highly connected transport factor. But we would like to know how to we would like to now I move on to validation of the network. So in we collect available for the genetic screening, we collect available mutant sources from ABRC and post-compiler gene enhancer trap. We almost collect more than 500 lines and we try to screen it and isolate loss of function mutants. So as you see here, first we just isolated loss of function mutants. Most of them we try to isolate the exon insertion. And then 90%, 97% have molecular phenotype in single loss of function mutant. And but only 3% of the mutants have short group phenotype. We find 2 mutants out of 60. Maybe this is because of we don't have enough pool of the mutant sources, or there is a gene is redundancy, so that's why we can't find any of the gene phenotype mutant phenotype in a single loss of function mutant. Anyway, I don't want to talk about more about this specific mutant, but I just move on more about this validation of the network. So even though this is indirect way to validate the genome-related network, we want to using the check the expression of the microRNA expression in loss of function, single loss of function mutants. So we use standard RT-PCR microRNA assay in compared with the wild type and mutant background. As you see here, we check more than 20 microRNA expression in a different mutant background. So 70% of the microRNA have a molecular phenotype. And even this is multiple transport factor is binding to the one single microRNA promoter. One of transport factor acts as an activator, the other acts as a repressor. So what we find is 35% of the transport factor function as a repressor, 35% is act as an activator. And we also want to check in vivo validation more. What we can do is we use a Tabacco system because a Tabacco system is very it's a system to identify the repressor or suppressor directly. We made two different construct. Effector is a transcription vector, and reporter is we just use a bus and then fuse with a specific microRNA promoter. So we pour infiltration into the Tabacco plant and check the possibility. So as you see here, if we microRNA promoter itself and then adding to the DOF, and then you can see that we reduce the gas activity. So maybe the DOF1 is function as a repressor. Till now we have 4 different constructs. They have a repressor function. And also we want to check about localization because some transport factor is novel, is not published at all till now. So we want to check the localization of the transport factor using the Tabacco system. As you see, we check the 14 transport factor transport into the Tabacco and check the localization. As you see here, 12 out of 14 transport factor, most of them localize in the nucleus, but 2 transport factor localize in the cytoplasm and nuclei. Might be another functional role in the cytoplasm function. Until now, I'm talking about individual checking the microRNA, individual interaction in a functional restriction and activator, I find. But for more system level approaches, we want to do, we use the genome-wide RNA-seq and small RNA library to globally monitor the expression of the microRNA and target of this gene regulator network. So when we're screening at that time, the GBF3 is kind of high interactor. They have 7 interactor, and they have different microRNA and transcript factor they are binding. And then using the small RNA library, what we check is they are differentially expressed in the 57% of the target is differentially expressed. And also we want to check the target of the microRNA using the RNA-seq data analysis, as you see here. 37% of the target is differentially expressed in a single loss of function unit. So we just validation of this gene regulator network. Now I move to functional characterization of the transcript factor. So in the gene regulator network, as I told you before, we generate a huge data set like this. But I told you this is 52 transcript factor family. This is huge data with a lot of transcript factor. But interestingly, some transcript factor is very enriched in our gene regulator network. As you see here, what we find is AP2ERBP, and then zinc finger homeobox transcript factor and the C2H2 transcript factor family. So this transcript factor is very highly connected to each other. So mostly I'm interested in one of these transcript factors, zinc finger homeobox transcript factor, because zinc finger transcript factor is one of the highly connected transcript factors because we just draw like separate cell network and draw the gene, which is cytoscape into another zinc finger homeobox gene regulator network. Because zinc finger homeobox transcript factor is quite interesting because in Arabidopsis thaliana, and there is relatively few gene families, it's 16 members. But based on our library, transcript factor library, what we find is based on the E1 hybrid system, there's quite higher interaction. So there's quite a lot of numbers, more than 10 interactions. So at that time, I thought it was quite interesting. And not only in the E1 hybrid system, using the E2 hybrid system, they are quite highly interact each other as a homodimer or heterodimer. So based on this, I was excited to screen the single loss of function mutant at that time. And the genetic screening at that time, none of the single have a phenotype. So I was so disappointed at that time. And then at that time, I tried to generate the double loss of function mutant. Finally, double have a little bit short root height, plant height, and also a little bit limb number is increasing. And then the cellular level is slightly in the Fe number. In the Arabidopsis sleep, there's a cell size is slightly reduced. But what I want to focus on is just branching number. It's like not clear in double loss of function mutant. It's like slightly enhanced branching number in vegetative tissue. So none of them have a phenotype in single double loss of function mutant in root phenotype. So I checked the expression. So as you see here, this family, interestingly, they are not that much expressed in the root, but they are quite high expressed in the young flower and old flower. So we use gene trap line as we check the loss activity. As you see here, the root, interestingly, not expressed that much, but there is vegetative tissue and shoot apical meristem and young leaf, all of them, they are quite expression. And then we also check the EFP browser to check this family expression. As you see here, it's a similar result. As the shoot apical meristem and young flower is quite abundant expression and a little bit expression in embryo. And at that time, we generated double loss of function mutants. We will not think about multiple knockdown system. And so we collaboration with UCSD, Juliet Schroeder group, and then we generate the artificial microRNA to knock down multiple gene family. So at that time, I was quite interested because this is a similar result with a double loss of function mutants. As you see here, compared with the wild type and then artificial microRNAs in fingernail transfer factor family. As you see here, enhanced branching. But this is just the same stage at certain states, but as time goes on, more severe branching occurs. And also they have a distorted flower structure, like not open, the petal is not fully open, and then there's a little bit twisted shape they have. And then finally they have still is dramatically reduced, and then I can get seed properly. There's a few seeds inside of the cell. And there is anyway, there is enhanced branching. But the gene is 5 gene is lost reduce the expression in the artificial microRNA line. And then we have another approach because we didn't know that this is working in our system. So collaboration with the Japanese group, and they use a different repressor transgenic lines. Because what they use is they use a genetic repressor silencing technology. They put ear domain stroke repressor at the end of the gene, and then back to the transformation in the wild type, and to see there is multiple gene families now. So as you see here, we use two different gene sets, and this is more severe phenotype compared with artificial microRNA. And they have very dark vision, but as time goes on, they have a lot of branching. So this is very consistent. But now you can ask me why we're talking about the flower and vegetative tissue, because you are initially, project is a start in the root phenotype, right? Root Arabidopsis transverse factor family. Now back to the root again, because single, double, triple, none of them have finally quadruplet generated, and artificial microRNA have reduced. And the interesting thing is, we overlapping with expression profiling, tissue-specific expression profiling with microRNA data, as you see here, except one finger box transverse factor in the root. Without that, 6 out of 7 transverse factor is very enriched in the same tissue cell types in the mature data. That is quite interesting. And next, our question is, what's the common target of this gene finger transfer factor family? So we draw again, like all the hierarchy system, gene-regulatory network. And this is all gene finger transfer factor promoter, and this is transfer factor family. As you see here, so these 3 microRNA is very common target of our gene finger transfer factor family. It's not clear here, but microRNA 167, 393, 163. So you want to briefly check the expression of the microRNA, and what we see is microRNA 393, 168, I'm not sure, slightly different, but I checked the microRNA 167 in the written background, they are reduced expression. But also I checked the target of this artificial microRNA target is R6 and 8. This is a little slightly off in the written background. So we think that really this gene finger is binding to this specific microRNA promoter, because we have this own in vivo system in vivo histone hybrid data. So prove this in vivo validation, we use chip qPCR. So we generated a GF fusion transgenic lines, and we get a transgenic line. And this we check the expression, we should choose a high expression transgenic lines. And then as you see here, about after immunoprecipitation, and then compare with IgG as a marked line, as you see here, P2 promoter region is enriched in the overexpression line. So we think HB34 binding to the microRNA 67C. So before I mentioned about the East2 hybrid analysis, but based on East2 hybrid analysis, they seems to binding each other. So validate for this, we use a protoplast system to construct different VIFs construct, whether they're really binding, and then they can get a signal, especially in CFP signal. So in case of the control, as you see here, GFP localized in nucleus cytoplasm, and then HB33, 34 construct, and then transform into the protoplastic, and then incubation, and as you see here, they are localized in nucleus. They are binding, and then CFP. And then HB33, 31 seems like localized rice in the nucleus is binding as a homodimer, and then they have in the nucleus. So now we have a proposed model in the microRNA of 22 model. So as you see here, we have a lot of single transcription family, but we don't know yet how they are interact in vivo, in the real, in the binding. But we try make a construct into the validation. But they are binding each other heterodimer as homodimer, binding to the microRNA 167 promoter and other microRNA promoter, and then activate or repressor of microRNA expression, and then negatively, repress of the R6. This is target. The other is other microRNA target, and finally they have a short protein. So maybe the other oxane and the NAC, the other mutant, the other hormone is might impact, but this is further study on this project. And the next one is I want to briefly mention about. I'm still talking about Arabidopsis thaliana as mother plant, but I just only be mentioned about how about the other crop species and other lower plants. So in our lab, mostly working on the Arabidopsis, but maize and sorghum we are still working on. So at that time, I didn't expect the phenotype in the maize, corn phenotype, because in the Arabidopsis there is multiple gene knockdown system, and then we have a phenotype. But interestingly, in maize, there are we got a new insertion line here, and then last summer we just planting a farm. I didn't that much pay attention, but finally there is a top feature slightly and enhanced branching in the field. And then we did the genome typing. This is phenotype, so we are quite excited about this. And then check the expression of the non-Q teller expression, and then we wanna check overlap with the QTL analysis. And as you see here in maize, they are quite high expressed in the ear, and also the shoot apex. And then a lot of different inbred line in our population, two gene flood system, they still have a lot of ear expression and then shoot apex. And interesting thing is, this is really involved in QTL locus. So we just using the Brahmin website and check the QTL locus compared with this gene locus. And interestingly, we find a lot of locus in this region. So first, we find the flower, the ear diameter, ear height, and ear length. This is directly related with the crop yields, so we are quite interested. Also, there is plant trait. So this year we have a plan for a lot of generation multiple knockdown system too, and then overexpression line generation, and we'll see how it's going. And then this is similar phenotype across the species, Arabidopsis and maize, and how they are conserved each other between Arabidopsis and maize. So this is projected maize gene regulatory network using the Arabidopsis also loss gene in maize. So this is huge data here, but we find it, and then more than 36,000 interactions we find it. And then based on this, what we can do is, this is preliminary data, but we have quite exciting result. So we kind of switched the promoter each other, but it's not clear. But in case of HV33 and 34, they are quite binding specific microRNA. So in case of the we use microRNA 393, they are binding to the Arabidopsis microRNA 393. Also, they are binding to the maize microRNA 393. And also, we are swapping in the maize transcript factor and same transcript factor binding to the Arabidopsis and maize promoter is the similar result, but not all. So till now, we have conservation almost 67% in germ. So we can more screening, and then how this evolution is conserved, the promoter region and the gene function annotation, we can further study. And I will more briefly mention about one of these things. So I will talk about Arabidopsis, now move on maize. But how about the evolutionary aspect? So I'm quite interested in the gene-finkel homeobox transcript factor is conserved across all species. The question is no. But as you see here, it seems like all conservation in these plant spaces, we collect 82 species, and then they are almost conserved in every species. But I cannot get any sequence from moss in the lower plant, moss, and ocean plant, and then green algae and red algae. So it's quite interesting. So I just go back in the more identification of the distinct finger transfer factor in plants. So it's, but I'm not a expert in this area, but it seems like from the ancient ancestor, the flowering plant, they have only exist in from the moss and river. So it seems like adapting finger in the box transfer factor it arises from plant tradition from ocean plant to land. So now we just wanna do more like molecular mechanism, and then we are working on most a little bit about this, and we can see how the results. We just clone the most recently most gene, and then wanna transform it to adaptations, and then they can functional similarity they have and the conservation between the gene. Moving forward, I would like to leveraging this system, and till now I'm focusing about the developmental aspect because we just screen the genetic screening and then isolation of the loss of function mutant see the phenotype. But I think the gene expression and the phenotype is not only the developmental things. I think the developmental, not only the developmental, but also the stress responses. So in plant stress is mainly in abiotic stresses, and we have a lot of data sets. So collecting all the expression profiling, microarray expression profiling, RNA profiling, we collect 25 stress categories and 400, more than 400 different conditions. So based on all this information, and we already have one hybrid analysis and the gene regulatory network, and we combine with three different approaches, and then we want to see how our gene regulatory network is functionally dynamic functional role in plant. So this is collaboration with Pioneer, and then now we're just screening about the mutant analysis, and then put the different stress condition, and then soon we have an interesting result related to the gene regulatory network. Now I want a summary and for future direction. So we identified the microRNA gene regulatory network and identified upstream almost 950 transfer vessels that regulate microRNA expression. We screen the use the genetic screen to identify the specific expression of the transfer factor. So we screened 60 transfer factor mutants, 97% of them, and 3% have real phenotype. And in vivo validation, in microRNA expression itself in a single loss of function mutant, 70% of microRNA is a molecular phenotype in single loss of function mutant. And half of them act as a repressor, half of them act as an activator. Also, system level approaches we did RNA-seq and small RNA library. So 57% of the gene and microRNA gene, and 37% of the microRNA target is differentially expressed in the higher connected single loss of function mutant. So I mentioned about the highly connected transcript factor. One is my main focus is thinking of the transcript factor. This is maybe the key role in developmental regulator. And now we think is core root of network for this transcript factor that can be expanded to the other different functions in different organs. So initially we start with the root, but we can expand it our gene regulatory network other tissue. I think I move on to the vegetative. Maybe there is a lot of flower and we can expand it other tissue. And the genome scale chipset experiment is going on because we have genome scale a lot of ISA data, ISA1 hybrid data we have. So combining with chipset data, maybe a more clear idea in vivo real target of the microRNA, and then upstream of the transcript factors. And also the last one is using our existing gene regulatory network. This we are moving forward with the system level approaches to use the identification of sub-network. So we have a lot of examples. Today I just want to mention about one sub-network, but we have a lot of different microRNA network and transport factor family network. So now we have level to colleague and doing that kind of different approaches using the different sub-network. So I would like to thank you about my PI, Dori Bear. She is a great mentor to drive a project. And Defy is mainly she's energetically working on this one hypersystem, analysis, and nature. She's sold a lot of screen she did, so several years, almost 4 years. And Jerry and Andrew is bioinformatician, so our lab is divided by two different parts: clear, naive bench person and bioinformatics person. So we needed communication to get a result of real biological question because they are almost computer scientists. So these two guys helping me to run RNA-seq and small RNA library, and iPlant also helping me to run an myself RNA-seq and small RNA library. And the other person is our genome-negative network group. So the rest of them is our labs members. And we have beautiful collaborator is US UCSD, Julian Schwer, and then Japan Masaru Group and Duke Philippine Group is initially project is going on. We have a new collaborator, Schwer Group. Thank you for your attention. Now I will take some questions.
Any question?
Can you go back one slide, please? Sure. Maybe the regulating